Welcome to today's Explainer. We are tackling something today that is, frankly, totally mind-bending. It's one of the biggest paradoxes in all of astrophysics. Think about it. We live in a solar system anchored by this immense thermonuclear reactor. Our sun has a core temperature of over 15 million degrees Celsius. It's an absolute inferno. Yet, if you step just a little ways away from that raging fire and out into the cosmic void, the baseline background temperature of the universe hovers at a frozen 2.73 Kelvin. That's about minus 270 degrees Celsius. So how is that even possible? How can a universe absolutely filled with stellar fire simultaneously be a freezing void?
Okay, let's dive into this. And we'll start with a rather surprising take from science communicator Bill Nye. He famously said, "Space is not all that cold. There is a fantastic amount of space in space. It's toasty." Now, I know what you're thinking. On the surface, that sounds completely absurd, right? But as flippant as it seems, this quote actually hits the nail on the head regarding a fundamental truth of statistical mechanics. It really hints at the sheer vastness and emptiness of space, and it's that emptiness that completely dictates how it behaves thermally. So, consider this for a second. If the sun is throwing off 15 million degrees of heat from its core and millions more from its outer corona, why on Earth, or rather, why in space, is the cosmic baseline a frozen 2.73 Kelvin? This cosmic microwave background, which is basically the leftover relic radiation from the Big Bang, forms the thermal floor of our universe. Resolving this ultimate mystery, how stellar fire and almost absolute zero just casually coexist, means we have to fundamentally rethink what we actually mean when we use the words hot and cold. To solve our paradox, we need to look at a crucial twist in physics. You see, in our everyday lives, we basically use the words temperature and heat as if they mean the exact same thing, but they are entirely different beasts. Temperature is just a statistical measurement. It measures how fast particles are vibrating and moving around, their average kinetic energy. Heat, on the other hand, is the actual transfer of that energy from one system to another. And here is the mind-blowing reality of space. Without enough physical matter to actually transfer that kinetic energy, having a high temperature is completely meaningless.
Now, what's really interesting here is the staggering drop-off in particle density once we leave Earth. Down here at sea level, just 1 cubic centimeter of air has around 27 quintillion particles. They are constantly bumping into you, transferring heat. But look up at the solar corona. The particles there are moving so incredibly fast that their kinetic temperature translates to millions of degrees. However, the density is super low. If you were floating in the solar corona, assuming you could magically get there, you wouldn't instantly vaporize from the ambient heat. Why? Because there are literally too few particles to strike your body and transfer that thermal energy to you. And out in interstellar space, the density drops to a mere 1/10 of a single particle per cubic centimeter. The vacuum effectively has no temperature of its own because, well, there's practically nothing there to measure.
Since space is, for all intents and purposes, empty, we have to look at the 3 ways heat actually moves to understand how things get hot or cold out there. Number 1 is conduction, which happens when matter directly touches other matter. Number 2 is convection, which needs the flow of fluids or gases. And number 3 is radiation, traveling as electromagnetic waves. Now think about the vacuum of space. Because there's no matter, conduction and convection are physically impossible. They're off the table. That leaves radiation as the one and only thermal exchange mechanism for literally any object out there.
If this all feels a little abstract, you probably have the perfect example sitting right in your kitchen, a vacuum flask. You know, like a thermos. A thermos has a double wall, and the air is literally sucked out of the middle to create a vacuum. That empty gap stops conduction and convection dead in their tracks, which is why your coffee stays hot and your water stays cold. To stop that final mechanism, radiation, the inner walls are made highly reflective. As you'll see, surviving the cosmos means engineering spaceships and spacesuits that act exactly like your morning thermos.
But what happens when you're way, way out there, far away from a star? Because radiation is the only way heat moves, distance is a huge deal, all thanks to the inverse square law. By the time the sun's electromagnetic radiation reaches the deep interstellar distances, it dilutes geometrically across the sheer vastness of space. Out there, a 1 square meter object receives only 13 billionths of the energy emitted by a simple 1 kilowatt household space heater. Without a nearby star to top up its thermal reserves, any object is just going to continuously radiate its own heat away into the void until it freezes right down to that 2.73 Kelvin baseline. So proximity to a star gives you the energy, but what you actually do with that energy is the real game changer. Just compare the Earth to the Moon. Earth is wrapped in this cozy atmospheric greenhouse effect. It traps incoming solar radiation and buffers our temperatures, so we only get pretty mild daily shifts. The Moon, though, it's an airless vacuum. It has no thermos blanket whatsoever. In direct sunlight, the surface just absorbs radiation unrestrained, and the temperature spikes to a blistering 121 degrees Celsius. But the very second it rotates into darkness, that heat just radiates instantly back into space, plummeting the surface down to a staggering minus 184 degrees Celsius. It's brutal.
And the International Space Station deals with those exact same crazy microclimates. It orbits Earth every 90 minutes, meaning its sun-facing side cooks at 121 degrees Celsius. Then it sweeps into Earth's shadow, and the exterior temperature immediately plunges to minus 157 degrees. But here's the cool part. The average exterior temperature actually stabilizes around a totally comfortable 10 degrees Celsius. How does that work? Well, because its 90-minute orbit is so fast, it's only in darkness for about 45 minutes at a time. That simply isn't enough time for the station's massive thermal inertia to completely freeze over before it bursts right back into the sunlight.
But surviving space isn't just about giant metal stations. It's about protecting the incredibly fragile human body. So the crucial point here is a horrifying physiological reality known as ebulism. In the absolute vacuum of space, the lack of atmospheric pressure causes the boiling point of liquids to drop dramatically. Without protection, an astronaut's blood and body fluids would literally begin to boil at temperatures below their normal 37 degrees Celsius body heat. Dissolved gases would rapidly form bubbles, causing massive embolisms, and you'd lose consciousness in about 15 seconds. Definitely not a good day at work.
Obviously, to prevent ebulism, we have to put astronauts in pressurized spacesuits. But you can't just pump the suit up to Earth's normal sea level pressure of 14.7 psi. If you did that, the vacuum of space would pull against it, inflating the suit into a totally rigid balloon. The astronaut wouldn't even be able to bend their arms or legs. To solve this, NASA pressurizes the spacesuit, or extravehicular mobility unit, to a very delicate 4.3 psi using pure oxygen. That hits the perfect sweet spot. It's just enough pressure to stop your blood from boiling and keep you breathing, but low enough to actually let you move your joints and get to work.
Let's see how all these layers come together to create what is basically a wearable spacecraft. A modern spacesuit is the ultimate expression of our thermos analogy. The outermost layer is made of white orthofabric to bounce away visible solar radiation. Then, the middle layers are this multi-layer insulation made of aluminized mylar to trap heat and block radiation. Closer to the skin, urethane-coated nylon holds in that vital 4.3 psi of pressure. But here is the crazy catch-22. Inside this incredibly well-insulated thermos, an astronaut doing heavy physical work generates up to 2,000 BTUs of metabolic heat. Without a way to vent that, they would quickly overheat and die in their own thermal trap. And that is exactly where the innermost spandex layer with embedded tubing comes to the rescue.
That spandex layer is called the liquid cooling and ventilation garment. It flows chilled water directly over the astronaut's skin, absorbing their metabolic heat through conduction. But then, how do you dump that heat into a vacuum where convection doesn't exist? You use something called a sublimator. Feed water freezes inside the microscopic pores of a metal plate that's exposed to the vacuum of space. The warm water from the astronaut's suit flows past this plate, melting the ice. Because that melting ice is exposed to a vacuum, it sublimates, meaning it flashes instantly from a solid right into a gas, carrying all that thermal energy out into the void. It is a brilliant, ultra-efficient air conditioner, but there's a heavy penalty. An astronaut boils away about 3.6 kilograms of water every 8-hour spacewalk just to keep cool.
All right, we've seen how humans handle Earth orbit, but let's shift gears to the absolute extreme frontier of thermal engineering. I'm talking about the Parker Solar Probe. This is a human-made spacecraft flying straight into the outer atmosphere of the Sun. At its closest approach, it literally dives through coronal plasmas measuring over 1 million degrees Celsius. But remember our rule about particle density from earlier? Because the density is so low up there, the ambient kinetic heat isn't actually the threat. The real danger, the thing that will melt the probe, is the intense, blinding solar radiation firing directly at it.
To survive that gauntlet, engineers designed the ultimate shield. The thermal protection system is a massive 8-foot-wide shield made of a 4.5-inch carbon foam core, sandwiched between carbon-carbon face sheets. The very outer coating is bright white aluminum oxide, layered over a microscopic tungsten film. It essentially acts as a hyper-advanced mirror, violently reflecting incoming solar photons back into space before they can even be absorbed into the ship. Of course, a few sensors, like the solar probe cup, have to peek out beyond the shield, so those are forged from exotic titanium, zirconium, molybdenum alloys and tungsten to keep them from melting into literal slag.
And this brilliantly illustrates the utter mastery of modern thermodynamics. Just look at this stark contrast. The front face of the Parker Solar Probe's shield takes the full, brutal force of the sun, glowing red hot at a blistering 1,377 degrees Celsius. Yet literally just inches behind it, sitting perfectly safe in the shield's shadow, the highly sensitive scientific payload and electronics are humming along at a cozy room temperature equivalent of just 30 degrees Celsius. By strictly controlling radiative thermal exchange, we built a shield that perfectly separates starlight from shadow. It's just unbelievable.
Which brings us full circle right back to the profound truth of our stellar cosmic paradox. Empty space itself has no temperature. The heat we experience isn't a property of empty space. It's the result of electromagnetic radiation colliding with physical matter. Space isn't cold because it lacks energy. There are 15 million degree thermonuclear stars everywhere. Space is cold because it lacks matter to absorb that energy. Whether it's an astronaut wrapped in a shiny mylar thermos or a probe hiding behind a high-tech carbon shield, surviving the cosmos really comes down to one simple rule. You are entirely in control of your own thermal destiny. So if empty space is actually neither hot nor cold, what other everyday illusions of our universe are just waiting for a change in perspective? Thanks for joining me on this explainer, and keep your curiosity running hot.